Let's look at the concept of motional EMF. Let's assume you have a rod, that one, the length of which is, say, L. And let's assume that this rod is moving to the right with some speed, v meter per second. Now we are dealing with a conducting rod here. And this conducting rod is situated and it's moving in a region where you have a uniform magnetic field. And the direction of this uniform magnetic field is represented by these dots. That means the direction of this magnetic field is coming out of the plane, or it is 90 degrees to the horizontal plane or the computer screen. Now we know this is a conducting rod, so you can expect some free electrons within that rod. Let's look at one free electron and see what happens to that electron. Now it carries a negative charge, let's say minus Q, Coulomb. So what happens is that you have a negative charge with a velocity to the right, speed is v meter per second, and the magnetic field in which it's moving is coming out of the plane. That means there must be a magnetic force acting on this charge, and it's given by QV cross the magnetic field. Now we note that this charge is negative, so let's write the charge like that. Next, let's perform this cross product. If you assume that the direction of the velocity is along the x-axis and the magnetic field is coming out of the board, so that is along the z-axis, and as you curl your right hand fingers from the x-axis, the positive x-axis to the positive z-axis, you see that your right hand thumb will be moving, or will be pointing downward in the direction of negative y-axis. However, since the charge is negative, the negative of that negative y-axis is a positive y-axis. So the direction of this magnetic force on this negative charge is actually going upward, like that. As time goes on and as the conducting rod keeps moving to the right in the magnetic field, more and more negative charges would accumulate at this end, the top end of that conducting rod, and that would make the top end negatively charged. The bottom end, as a result, will be more positively charged. Like that. So if you look at a typical negative charge at the top end of this rod, you see that there are two forces acting on this negative charge. One is the magnetic force that's pushing it upward, and the other one is the electric force that is attracting it downward. Let's call it Fe. And since that negative charge is stationary, the two forces balance out. The magnetic force in an upward direction is balanced by the electric force in a downward direction. So if we equate the two forces, magnetic force on that negative charge is equivalent to the electric force on that negative charge. We know the magnetic force is given by QVB, the magnitude of it, and the magnitude of the electric force is given by Q electric field, where this electric field extends all the way from the bottom end to the top end of that conducting rod, like that. So that is the electric field. And we see that Q cancels, and we have an expression for that electric field that builds up within that rod. It is quite simply the speed of that conducting rod times the magnetic field, the external magnetic field in which the rod is moving. We see that since these ends are of opposite charged, there is a potential difference within that conducting rod, and it is given by the electric field times the length of that rod. Since the electric field is given by that expression, the potential difference is quite simply given by VBL, like that. And this potential difference across that conducting rod exists as long as the rod moves through the field with this much speed. We see that this setup is almost equivalent to some kind of a battery. So this is a positively charged terminal of the battery. This is a negatively charged terminal of the battery, with the potential difference is quite simply the EMF of that battery. So this EMF that results from the motion of the conducting rod is known as the motional EMF. To avoid confusion, this V in the delta V is the potential difference. So let us use the capital V for that, and this V is the speed of that conducting rod. Let's make the moving conductor as part of a closed conducting path, like in this figure. As the rod moves to the right, it will trace out a certain amount of area, and this area is shaded right there. Let's call it A. Let's analyze the situation using Faraday's law. Faraday's law states an EMF results whenever there is a change in magnetic flux. And in this case, the change in magnetic flux with time is due to the changing area. The magnetic field remains constant. Also, if you look at this view of the system, the magnetic field is going like that, and the area vector is also going like that. So the angle between them is 0 degrees, cosine 0 is 1. What that means is the above equation will simply becomes minus b d dt A. Note that since the rod is moving with speed v, this length here, the additional length, is quite simply becomes vt, where t is the time it takes to cover this much distance. So the area A is quite simply Vt times L, this side times that length. Substituting this A in here, we get the EMF to be minus B d over dt VTL. V and L can be taken out of the derivative sign, giving the result minus BLV, because d dt t is 1. Now you see these two terms agree. Of course you have a negative sign here, and the reason you have a negative sign is because of the convention in the definition of Faraday's law. Let's work out the direction of this EMF. So you have a loop like that. The field is going that way. The area vector is going that way, and the area vector is increasing. So that means the magnetic flux is increasing with time, and the EMF should be negative. The negative direction of EMF from our sign convention means in that direction. So that is the direction of the induced EMF. So coming back to this view, that means the induced EMF is going like that, or quite simply like that. And this should also be the direction of the induced current, as we previously discussed. And this agrees with the fact that this end is a positively charged and that end is negatively charged. So the current should move from the positive terminal to the negative terminal as we expect. And now you can clearly see why this induced EMF is called motional EMF. And the reason is because it arises from the motion of a conductor through the magnetic field. Let's look at the following problem. In the figure below, the rod has a length of 0.4 meters. And it moves in a magnetic field with magnitude 0.8 Tesla. And the field is coming out of the plane. The EMF induced in the moving rod is 2.5 volts. You want to find the speed of the moving rod, that is this one right there, the induced current, if the total resistance in the circuit is 0.6 ohms, and also the force that the magnetic field exerts on the rod as a result of this induced current. We note that the direction of the induced EMF is given like that. So the direction of the induced current in blue is also in the same direction as the direction of the induced EMF. Now we know the expression for the EMF is, the magnitude of it is BLV. If the magnitude of the EMF is 2.5 volts, the strength of the magnetic field is 0.8 Tesla, the length is given to be 0.4 meter, we can calculate the speed, and it will turn out to be 7.81 meter per second. So that is part A. Now let's look at part B. We want to determine the induced current, and that can be determined from Ohm's law, EMF over the resistance in the circuit. If the EMF is 2.5, that's given, the resistance is 0.6 ohms, you see the current turns out to be 4.17 ampere. Next, the force the magnetic field exerts on the rod. The rod carries the current in this direction, so downward, so that's your current. The field is coming out of the board as represented by the dot. Magnetic force is given by IL cross B. So the direction of L is downward, following the direction of the current. B is coming out of the board. Taking the cross product between these two vectors will give you the magnetic force in that direction. So that is the direction of the magnetic force. Now the magnitude of that magnetic force is ILB, because the angle between the current and the magnetic field is 90 degrees, sine 90 is 1. So the magnitude of the magnetic force is the current, which is 4.17 from part B, the length, which is 0.4 meter, and the magnetic field, which is 0.8 Tesla. And that's going to give you 1.33 newtons. And the direction of this magnetic force is like that, to the left. Thank you for watching.